People say the golden ratio is hidden everywhere. In the Mona Lisa, the Parthenon, even nature itself. But is that actually true, or are we just really good at seeing patterns? So I tested the golden ratio to see if it is truly worth the hype. Let's find out. Alright, but what is it? The golden ratio, called phi, is a number defined in math as 1 plus the square root of 5 over 2. That comes out to about 1.618, and it's what's called an irrational number, meaning the decimal goes on forever. So what is the Fibonacci sequence, and how does that relate to the golden ratio? It starts with a 0 and a 1. Then each number is just the sum of the two before it. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and the pattern continues. These numbers are referred to as Fibonacci numbers. Okay, so how does this pattern connect to the golden ratio? As you go further down the Fibonacci sequence, when you divide a number by the one before it, the results get closer and closer to the golden ratio. For example, 3 divided by 2 is 1.5, whereas 8 divided by 5 is 1.6. But 377 divided by 233 is about 1.618, which is already very close to the golden ratio. As the numbers grow larger, the ratio between consecutive numbers gets closer and closer to the golden ratio. What's even more interesting is that this doesn't just work with Fibonacci numbers. For example, starting with 6 and 7, 6 plus 7 is 13, 7 plus 13 is 20, and so on and so forth. And when we divide two consecutive numbers, like 589 divided by 364, we get about 1.618. So again, we can see that as the numbers get larger, our result gets closer and closer to the golden ratio. This rectangle and spiral shape is often used to show the golden ratio in things, like the Mona Lisa, the Parthenon, and even seashells. But what actually is it? Let's go back to the Fibonacci sequence. Since I can't draw a 0 by 0 square, I'm going to start with a 1 by 1 square. Next, I'm going to draw another 1 by 1 square. Now I'm going to draw a 2 by 2 square. Now a 3 by 3 square. Notice how the 1 by 1 and the 2 by 2 square connect perfectly to the 3 by 3 square, since 1 plus 2 equals 3. Alright, now let's draw a 5 by 5 square. And we continue this pattern. As the pattern continues, the overall shape begins to approach what's called a golden rectangle. Now if I draw a curve connecting opposite corners of each square, we get this spiral shape, which is called a Fibonacci spiral. And this is what people often use as an approximation of the golden spiral. So is it real, or is it all just a myth or coincidence? The golden ratio, or phi, equaling about 1.618 is absolutely real. It's just another mathematical constant, such as pi equaling about 3.14, or e equaling about 2.718. And it shows up naturally in math. We saw it appear in the Fibonacci sequence, and it also appears in geometry. For example, in a regular pentagon, the ratio of a diagonal to a side is the golden ratio, about 1.618. So does it actually appear in architecture, art, and nature? Let's start with the Parthenon. Even though the Fibonacci spiral can be made to line up with it, there's no credible evidence it was designed using the golden ratio. The Parthenon was built around 447 BCE, while the earliest known description of a related geometric ratio appears later, around 300 BCE, in Euclid's Elements. According to Cambridge.org, the golden ratio was totally absent from Greek architecture of the classical 5th century BC, and only very rarely employed in the 3rd and 2nd centuries BC. Now let's look at the Mona Lisa. Again, the spiral can be made to fit it, but there's no solid evidence that Leonardo da Vinci intentionally used the golden ratio in its composition. What we do know is that he was a master of proportion as seen in his Vitruvian Man, and that he was familiar with the idea of the golden ratio since he illustrated Luca Pacioli's De Divina Proportione, a book centered around what we now call the golden ratio. But knowing about the golden ratio and intentionally using it in his art are two very different things. However, the spiral can be made to fit many other things, such as the Great Wave off Kanagawa, seashells, and even plants. So I wanted to test it out. If the golden ratio truly reveals some deep hidden structure in both art and nature, then it probably shouldn't fit just anything. Before doing any of these tests, I spent a few hours creating an accurate golden rectangle and Fibonacci spiral so I could use the same template on every image. I started with one of my dad's paintings because I know for a fact he wasn't intentionally using the golden ratio in his art. And honestly, it still lined up surprisingly well. Then I tested it on a few things in nature. Here is a spiral aloe. Seems to fit well. This conch shell. Again, the spiral seems to fit reasonably well. So I decided to get even more random. I found this splatter painting and somehow you could still make an argument that the spiral fits. Then I tried this pile of rocks, and once again, different parts of the image seemed to line up with the spiral. I wanted to get even more random, so I took this picture in the parking lot of my nearby grocery store without even looking at what I was photographing. This black car fits into this rectangle nicely, and this car on the left aligns with the spiral as well. At this point, I'm not convinced that the golden spiral by itself proves anything, because I was able to make it fit just about anything. So I continued searching for other examples of the golden ratio or Fibonacci sequence. Let's see what else we can find. Another place people often point to the Fibonacci sequence is in spirals in nature, such as in pineapples or pine cones. Let's start with the pineapple. You can see spirals going in this direction and this direction. Let's count the number of spirals going in this direction first. So in this direction, right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So in this direction, we get 13 spirals, which is a Fibonacci number. All right, now let's count the other direction. So starting from the top, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 spirals, which is not a Fibonacci number. Now let's test the pine cone. All right, let's count the number of spirals in this direction first. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 spirals going in this direction, which is not a Fibonacci number. All right, so now in the other direction, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 spirals in this direction, which is also not a Fibonacci number. So, in nature, these spiral counts sometimes match Fibonacci numbers, but not always. And depending on how you count them, you might get different results. Another example people often point to when discussing the golden ratio or Fibonacci sequence is flower petals. For example, lilies tend to have 3 petals, and buttercups typically have 5. Both 3 and 5 are Fibonacci numbers. I decided to take a walk around my neighborhood to see what flowers I could find. This flower I saw had 5 petals, and this daisy had 21. Both 5 and 21 are also Fibonacci numbers. At first, this seemed pretty convincing, but after looking into it more, I also found plenty of flowers whose number of petals don't match Fibonacci numbers at all. For example, this flower has 6 petals, and this one has 7. Neither 6 nor 7 are Fibonacci numbers. Similar to pineapples and pine cones, Flower petals sometimes match Fibonacci numbers, but not always. So, to summarize, the golden ratio, or phi, is absolutely real. It's a mathematical constant, about 1.618, that appears naturally in mathematics, including in the Fibonacci sequence and even in shapes like pentagons. But after researching and testing it myself, I think its connection to art, architecture, and nature is often exaggerated online. I went into this video with a completely open mind, honestly hoping it would be easy to find clear examples of the golden ratio everywhere around us. But the more I looked, the more complicated the picture became. Sometimes the patterns were genuinely interesting. Other times, it felt surprisingly easy to overlay the spiral onto almost anything. But whether or not the golden ratio is truly hidden throughout nature, I still think it's pretty amazing that such a simple mathematical idea can create patterns and shapes like these in the first place. But that's just my perspective, and now I'm curious about yours. Do you think the significance of the golden ratio is overhyped, underappreciated, or somewhere in between? If you found any other interesting examples of the golden ratio or Fibonacci sequence, I would love to read them in the comments. Thank you guys so much for watching, and until next time.